Hey everybody, let's greet each other properly. Good morning. This is Mr. Ainsworth, and we're going to get into a big subject called linear programming and how to apply systems of inequalities to a field of mathematics that is big. It was founded back in the 1940s by a few men. One of the co-founders and inventors was George Dantzig. He, with a group of guys in the 1940s, developed this to solve real problems in business, engineering, economics, and other parts of industry. After the lesson, you're going to be able to do a lot, and so let's go through a couple things. You're going to be able to formulate a linear programming problem from a real-life problem here, from contextual problems, all by yourself. Number two, you're going to be able to identify the feasible regions, which is the solution region. 3, you're going to be able to find solutions of the problem by graphing the system of inequalities. You're going to be able to not only graph the system of inequalities, you're going to be able to find the corner points of the bounded region, called the feasible region. You're going to evaluate the objective function, and you're going to be able to optimize the problem, which means you're going to be able to find the solution. And you're going to be able to summarize and state what it is. So let's get right into it here, and let's take a look at how George Dantzig and a few other guys took linear programming and solved problems in industry, also, problems involving diets too, by the way. And let's apply it to a variety of different situations. So turn the page and let's get started here. And let's first take a look at an agricultural problem. So check this out. A small firm or company builds 2 types of garden sheds. We're going to call them Type A and Type B. Type A requires 2 hours of machine time and 5 hours of craftsman time. Let's take this and organize this in the form of a table. We've got Type A here, and we've got Type B here. Okay, now it says Type A requires 2 hours. This should be hours, okay? Typo there. 2 hours of machine time and 5 hours of craftsman time. So let's put 5 in here. 2 hours of machine time, 5 hours of craftsman time. That means it takes 2 hours for a machine to build a Type A shed, and it takes 5 hours for a craftsman to build it. That's what it means. For Type B, that's a little bit different. It takes 3 hours of, these are hours now, of machine time and 5 hours of craftsman time. All right. Each day there are 30 hours of machine time available, no more. So only 30 hours or less can be used. So this represents a max. All right. And because of that, these are maxes in this case, there's only 30 hours or less available. So it's a max time. It's a limitation, max, or what's called a limitation. Now there's 60 hours of craftsman time. So 60 hours of craftsman time available. And that's a maximum too. So they can use 60 hours or less. You only have a certain time in a week, guys. It's not an infinite amount of time. So there's 60 hours or less available. These are limitations on the problem, which we call constraints. Okay. Now the profit for each shed is a little bit different. For Type A, it's $60. All right. For Type B, it is $84. So the profit or money they make, this is the money they make. That's called profit. Varies. $60 for Type A. And for Type B, it's $84. Those are the profit for each shed they make. So for one shed of Type A, they make 60. For 2, it's 2 times that. For 3 sheds of Type A, it's 3 times that, and so on. Likewise with Type B. So all we need to do now is formulate the appropriate linear programming problem, LP problem, and to maximize the profit. Okay, that's important. You want to maximize the profit and minimize the cost depending on these constraints or limitations. Another word for limitation is called constraint. It's a fancy word for limitation, but they use that word in linear programming all the time. So the two are synonymous, and you should get used to that. Constraint, limitation. The maximum, in this case, on the time available, because you only have so much time you can get on the machine per week. And the craftsman only works a certain number of hours per week too, so those become like maximums. So you can use the machine 30 hours or less than or equal to 30 hours. And for the craftsman, well, 60 hours or less. Because like I said, there's only a certain amount of time in a week that they could work. One of the things that you're also going to do in every single problem is define the unknowns. All right. So it says, what is the profit on each, or given these profits, how many of each type should be made? How many should be made? How many type A and how many type B should be made to maximize profit? In fact, let me write that down. So how many of each type, all right, should be made? Should be made, all right, to maximize profit? That's the big question in this problem. All right, well, we don't know. So we're going to say, hey, let x equal the number of type A here. Y equals the number of type B, number of type B. In fact, let's write them down here. Define the unknowns. Okay, number of type A shed. These are sheds now. You got to remember that. And Y equals the number of type B sheds. In any problem, there's going to be some unknown. You're not going to know how many to build of something or whatever the problem indicates. In this case, this is a shed problem. So, how many type A sheds should make? Given the fact that you get $60 for each one, and how many type B sheds, knowing that you get $84 for each one. But depending on these constraints, you don't know what to do to maximize your business. So what you learn how to do is model it or formulate the problem based upon your constraints. So what we're going to do is we're going to take them down here, and we're going to define the constraints and limitations. So check this out. We know that for every type A shed, it takes 2 hours of machine time. Well, we know there's a maximum available machine time of 30 hours. So what we're going to do is develop a constraint or limitation on the machine time given these numbers up here. So for every type A shed, it takes 2 hours. So for example, if we build one shed, it takes 2 hours of machine time. For 2 sheds, it takes 2 times 2 hours, or 4 hours. If we build 3 type A sheds, it's 3 times 2, or 6 hours. But in general, if we build X sheds, each one takes 2 hours here. It takes a total of 2x hours for type A shed for the machine time. So what we need to do is develop what are called constraints or limitations on the machine time and do the same thing for craftsman time. So going back up here, for every shed you make, it takes 2 hours of machine time. So the total time for type A, for machine time that is 2x hours. Well, if we build type B as well, every type B shed we make takes 3 hours of machine time. So if you build one type B, it takes 3 hours. Build 2, it's 2 times 3, or 6 hours. If you build 3 type B sheds, it's 3 times 3, or 9 hours. In general, you got to take your number of hours and multiply it by the number of sheds that you make. And we're making Y type B sheds. So you got to multiply 3 times Y. So 3Y hours for type B. But you have a limitation on machine time. There's only a certain available amount of time. And it states in the problem that it's less than or equal to 30 hours for the total machine time. Now you got a constraint on the craftsman time too. So here we go. For every type A shed, it takes 5 hours of craftsman time. It's time intensive. So for one, if we build one type A shed, it takes 5 hours. 2 type A sheds, it takes 10 hours for craftsman time. For 3 sheds, type A sheds, it takes 3 times 5, or 15 hours. But here I say we build X sheds, type A sheds. So what we have is 5 times X hours of craftsman time. So 5X hours just for the type A. For type B, we have 5 times Y because we're building Y of them. We've got to take the number of hours times how many you build, which is Y. So plus 5Y. And that's got to be less than or equal to the maximum number of hours you have in the week for craftsman time, which in this case is 60. Now, these variables represent sheds, and you can't have a negative number representing either one of them. The number of sheds cannot be negative for either one of them, so x has to be greater than or equal to 0, and y has to be greater than or equal to 0 because it cannot have a negative number for sheds. These are called non-negative constraints. Non-negative constraints, or the non-negatives. Okay, x and y can't be negative, so you make them greater than or equal to 0. You saw me graphing these in the previous lessons, so they shouldn't be that hard to graph. Now, in any linear programming problem or any LP problem, you're either going to maximize or minimize something. And in this case, we're going to maximize the profit. Okay. Now, because of that, for every type A shed we make, we get $60. For every type B shed we make, we get $84. So you got to take the amount of money you're making for each one and multiply it by how many that you make. If we make X of them, we have to take 60 and multiply it by how many you make. And then we got to take 84 and multiply it by how many you make. And that'll give us our total amount of profit that we make for both of them combined. This is called the profit function, or what's called in general, it's called the objective function. So your profit P is going to be equal to the amount of money per shed times how many you make, so 60 times X, plus the amount of money for the type B, $84, times how many you make, so 84 times Y. And that's called our objective function because our objective or goal in the problem is to maximize the profits. In fact, let me put maximize right here. Okay, we want to maximize the profit. How big can we get? We want to make money, right? So you want to maximize it. So what we need to do now is graph each one of these constraints. They're called constraints or limitations. All right, same thing. And over here, and find the feasible region and the corner points, because the corner points are the possible solutions to every programming problem. So what we want to do is we'll take the, we'll call this equation 1 here, and we'll call this equation 2. Equation 1, 2x plus 3y is less than or equal to 30, and we're going to solve for y, isolate y, and so we can graph it. All right, so what we have is, let's subtract 2x here, and we get 3y is less than or equal to negative 2x plus 30. Divide everything through by 3, and you get y less than or equal to negative 2/3 x plus 10. So my slope is negative 2/3 and my y-intercept is 10. And I shouldn't have any problem graphing here. This is 2, 4, 6, 8, 10. Plenty of room on the y-axis there with a y-intercept of 10. And this is 2, 4, 6, 8. Just writing these numbers a little bit bigger so you can see them. This is on the x-axis. This is the y-axis. Okay, now my second equation is 5x plus 5y is less than or equal to 60. I got to subtract 5x. Once again, you know, there's a couple different ways you can do this. One way is to isolate y and get in the slope-intercept form. And to do that, you have to divide by 5 afterwards. All right, and you get y less than or equal to negative x plus 12. 60 divided by 5 is 12. All right, so now what do we do? So my slope here is negative 1, and my y-intercept is 12. So let's graph these one by one. So first one, y-intercept 10. This one's going to be in blue. Down 2, right 3. Down 2, 1, 2, 1, 2, 3. 1, 2, 1, 2, 3. 1, 2, 1, 2, 3. You keep on doing this. You go down 2, right 3. Down 2, right 3. All right, and then you graph the function. So let's go ahead and do that. All right, and we want to graph the inequality here. And it's less than or equal to, so solve them below. Okay, and this is number 1. Number 2, let's do it in red. This y-intercept is negative, or is 12, and the slope's negative 1. So we're up here at 12. down one, right one, down one, right one, keep going, down one, right one. Oh, they intersect right there. Alright, so I can already see the intersection point right there. That's important to know, because we're looking for corner points, right? So you have to know where they intersect. Okay, and this one's down as well, because it's less than or equal to. Now for your non-negative constraints, this one right here, x greater than or equals 0 is always vertical. It's a vertical vertical boundary line. All x values greater than 0 are like 1, 2, 3, 4, and so on to the right. The horizontal boundary line here, this is a horizontal one. Alright, and that's y greater than or equal to 0, so it's started on the y-axis. Y greater than or equal to 0 is 0, 1, 2, 3, 4. All these y values are above the x-axis, so this is y greater than or equal to 0. The question is, where do these overlap? So it's pretty obvious, right? Where the green, the gray, and the red and the blue all overlap is in through here, and this is called the feasible region now. Feasible region in linear programming is a fancy name for the solution region. The region where, in this yellow region right here, is where all the points satisfy all the inequalities. Lucky for us, though, we have a theorem in mathematics that states that the corner points are the possible solutions to the linear programming problem. So all we need to do is find the corner points. That's this part right here. Using the vertices right here, or the corner points, evaluate the objective function to be either maximized or minimized. In this case, we want to maximize it. We'll do that in a minute. Okay, but again, the vertices are right here, this one, and that's, we'll call that point A at 0, 10. There we go. 0, 10. And then this one here, at 6, 6, we'll call that point B here. And then this one here at 12, 0, we'll call this point C. C at 12, 0, and that's right here. So we have, and then we have this one here. We'd use it if we needed a minimum. That's not going to give us our max because we've got to build something here. So I'm not concerned about 0, 0 because it's not going to maximize our function. All right, so our corner points that we're really concerned with is 0, 10, 6, 6, 12, 0, and, well, okay, I'll call this point, I'll do it just for funsies here, 0, 0, our origin. It's not going to be a good solution, though, because that means that we don't make anything. All right, so I'm really concerned with A, B, and C, these corner points here. Which one maximizes our profit function? They're all solutions to the inequalities. They all satisfy our constraints, but which one maximizes the profit and tells us how many type A sheds we should build and how many type B? All right, so let's go ahead and substitute these vertices into the objective function. Now, the objective function is the profit is 60 times x plus 84 times y, where x stands for the number of, it's right up here, type A sheds, and y stands for the type B sheds. So I'll put A here and B here, just so that it reminds me type A, type B. Okay. And the vertices, let me see, what are they? So 0, 10, so A is 0, 10, B at 6, 6, C at 12, 0, and we want to find the profits for each. So we got to take all these values and just substitute them in. That's what it means to solve a linear programming problem. The max and the min always occurs at a corner point. So 60 times 0 plus 84 times 10. What is that? Well, we've got that's 0, and that's 840. So $840 profit there. If we build 0 type A sheds, and this right here is type A, and that's type B, 10 type B sheds. Now, what's the profit here? We've got 60 times 6 plus 84 times 6. That's 360 plus, let me see, 84 times 6. That's 840, no, excuse me, 480 plus 24, 504. So, right here, let's just do this. 48 plus 2, 50, 504. So 504, 360, that's 864. So $864 there. Ooh, it's a little bit higher profit. And this one here is 60 times 12 plus 84 times 0, that's 720 profit. So what's the biggest profit? We want to maximize, of course. It looks like right here. But what will give us our max? It's this solution here. We need to build 6 type A's and 6 type B's, equal number of B's. It doesn't always happen like that. So our best solution here, our optimal solution, is that we should build, we should build 6, all right, type A and 6 type B, all right, to gain a maximum profit. Okay, profit of $864. If we do that, we'll get max profit. If we do anything else, we get less profit. And you can test it. You can pick any solution in here you want in the yellow area. Test it in your profit function, and it will be less than 864. So what's cool about this this problem here is that given the constraints of the problem up here, given all these constraints and limitations of machine time, craftsman time, and also the profit margins on each shed, we can optimize the problem, which means we can figure out how many type A and how many type B we should use to gain maximum profit. Pretty awesome. That's problem 1 of 5, and in the next video I'll go over problem number 2.